All right, so we are talking about, so we already did square threaded screws, and now we've moved on to bearing friction. And I broke that up into two. The first one is the one that we did, is thrust bearings. Can you think of like a physical example of thrust bearing friction? Uh, well, I was going to say like the clutch of a car is like that, you know? Um, yeah, you're probably right. I don't have no idea how a car. Okay, yeah, okay. Um, so this is what we've done so far, and then the second one is um, journal bearing or axle bearing. This is like when you have some kind of axle rotating inside bearings. So we'll get to that in a second. This is the one that we've done so far. So let me just start with an example. So let's say that we have a solid shaft that's rotating at a constant angular velocity this way. And let's say that the total normal force between these two, between the shaft and the ground, is, let's say that's 10,000 newtons. And let's say that this is a circular cross section with a radius of 0.1 meters. What's the couple, the external torque required to keep the shaft rotating with a constant angular velocity? And given that the coefficient of static friction is 0.0, let's say it's higher, 0.1, and the coefficient of kinetic friction is 0.06. Okay, so first of all, which of these two coefficients of friction is going to matter for us? Yep, that's right. So it's already rotating. So we care about the kinetic coefficient of friction. And now we're going to use these numbers and just go through the same integral derivation that I went through yesterday, basically. All right, so this is the cross section. This whole radius is 0.1 meters. The distance out to this arbitrary infinitesimal ring is r. That's our variable. We're going to integrate over these rings. So the first thing we have to do is figure out how much pressure each one of these rings gets. Well, not sorry, we're going to figure out the pressure so that we can figure out how much total normal force each one of these rings has acting on it, okay? Because the amount of normal force that any area gets is dependent on that area, okay? So the pressure is equal to the total normal force divided by the total area. In this case, the area is pi times 0.1 squared, so 10,000 divided by 0.0314. Can someone divide that out for me?
Or wait, 318,000.
310, call it. And what are the units of pressure? Pascals or newtons per meter squared. I guess it's always, the SI units is pascals, but let's think of it this way because that's going to help us as we go through this derivation. And so now what we want to figure out, based on this pressure, is the increment of normal force that's taken up by this infinitesimal ring. Okay, so how do we get that? Okay, I'm going to number these steps because you can just always follow these steps, First thing, get the pressure. Second thing, multiply the pressure times the increment of area to get the increment of normal force. So dN is equal to the pressure times the increment of area. What's this increment of area? For this, well, yeah, but just think of this thickness. So this is the part where you think of taking that little ring and unrolling it. The thickness is dr, okay? So the thickness of this infinitesimal ring is dr. So the area is the circumference times dr. We're thinking of unrolling it and making it a long, thin rectangle. That is, I mentioned this before, but I don't know, five more times in your engineering schooling, there's going to be some important derivation where where that's the way to think about it. So again, like if you keep that in mind, the next time it comes up, raise your hand. Everyone thinks you're smart, Yeah, right. You don't get that many chances, so don't squander them. Okay, so 318,310 times 2 times pi times r, that's a variable, dr. And so can someone multiply that out for me? Just the 318,000 times 2 times pi. Like exactly? Wow, weird. Okay. So that's the normal force. What's the next step? Step 3. So the next step is it's sort of like a trivial step, but just remember that the thing producing that moment isn't the normal force. That's like in the wrong plane. That's perpendicular to what we want. What's producing that is the friction force, which comes from multiplying the coefficient times this. So the increment of the friction force is 0.06 times, so it's the coefficient times the normal force, or times the increment in normal force. And so that's 0.06 times 2 times 10 to the 6 RDR. And so that is 1.2 times 10 to the 5. Yes. Sweet. So that's the increment of friction force, and now what we want is an increment of moment. So the fourth step is that the increment in the moment is equal to the moment arm times the increment in the friction force. So that's R times 1.2 times 10 to the 5th RDR, or 1.2 times 10 to the 5th R squared dr. Yeah. So now we have the final increment that we want. I mean, basically, the fifth step is, now that we have the increment in moment, we obviously want to just, so the total moment is just going to be the integral over that whole surface area of the increments in moment, right? Which, to us, we're integrating with the variable r. So we're going to go from, so this is going to be 1.2 times 10 to the 5th times the integral of r squared dr, and what are the boundaries of this integration? 0.1, exactly. And so you get 1.2 times 10 to the 5th times r to the 3rd over 3 from 0 to 0.1. And so you get 1.2 times 10 to the 5th, 0.1, so that's 0.001 over 3. And so that is 4 times 10 to the 2nd. 40 Newton meters. Okay? So it's those same 5 steps every time.
Can we come up with that generally and then like all of them?
Yeah, sure, that's fine. Yep. Mm-hmm. Any questions about that? Yeah.
The friction force is the coefficient, friction times
The normal.
normal force.
Right. Yep.
So
Yep.
we do have to prove this before we can use it.
Yes. Yeah, so don't just use that formula. You have to do this derivation. Yep.
But just, so we have to just go through these steps.
Right.
We don't
That's all.
write it out general, okay.
You can do it general or do it with the numbers. Either way is fine.
Another question, like
Mhm.
conceptually, these two types of bearings, they're not bearings in like the sense you think of them before this class. It's just two points rubbing on each other and creating friction, right?
Right.
So that's all that's going on, is just two things rubbing on each other.
In a circle. Yeah. Yeah. So that's the difference between this and like and like a block. The thing is, the fact that you have that rotational motion is the reason that every ring has a different, produces a different moment. And that's why you have to go through the integration and stuff. Any other questions? Okay. So that's it for thrust bearings. So now we're going to do journal bearings. And so you can think of these problems as an axle so this shaft is rotating inside, you know, this hole that goes through the bearing. The weight of something is split evenly over the two sides. So you have weight over 2 on one side, weight over 2 on the other side. And given the coefficient of friction, we want to, again, find the moment that has to be applied, the torque that has to be applied to the axle that's required for either maintaining a constant angular velocity or a second to initiate motion. And the only difference between how you treat them is which coefficient of friction you use. So to do these problems, draw a free body diagram of a, so draw the free body diagram of the axle, and we're going to look at it from the side, like over here, you know. That's what my 3-year-old looks like. So this is the view we're going to take. All right, so what loads are acting on the axle? Well, there's a W over 2 here, a W over 2 here, but since we're looking straight on, that just ends up being a downward force this way. Okay, and let's say that this is, so let's say it's rotating like this. Okay. So the motion is this way. In either one of these two cases, this is in static equilibrium. Well, yeah, I mean, there's no angular acceleration. So there has to be an upward force of W. And that's provided by the bearing, right? The question is, where does that act? And where that bearing force acts determines what the moment is that's required. So remember that if this opening fits well for this axle, there's pressure at every point, right? Every point around this circle. But you can think of it as like a distributed load that varies as you go around. You know, the distributed load is greater at some points and smaller at some points. And so even though every point is touching, if you represent the total force applied by the bearing as an equipolant system where you only have one total force acting, that can move around depending on what the motion is because the distributed load changes. If it's going this way, the effect is that the point of contact moves. It's like, you can think of it sort of as like this axle trying to kind of climb the wall due to the friction. Okay, that's not really what's happening, but that's the effect that you have. And so you get a force from the bearing that looks like this. And so what we have to do is we just have to, so notice that our task here is to figure out what the moment is that this force from the axle applies about the center of this, or the force from the bearing applies to the center of this axle. If we can figure out what that moment is, then that's also the moment we have to apply in the other direction to keep it rotating with a constant angular velocity. Okay? And so this is just going to be like some trigonometry stuff. Does everyone sort of follow what the... Yes. Okay, so it's an experimental fact that if you calculate the center of pressure of all of the full distributed load applied to the axle by the bearing, if it's rotating this way, you get a total bearing force that moves in such a way that it provides the opposite moment. So think of it like this: like you know that friction from the bearing is going to slow down the motion, right? That's the effect it's going to have. So if the rotation is this way, okay, if the rotation is clockwise here, the force from the bearings has to move in the direction that provides the opposite moment. So you can see it here. Like if you apply this force here, it has the tendency, if your about point is the center of the axle, to rotate it the other way and to stop the motion. Yep. The same, it's just the same thing, because if it's at rest and you're trying to figure out a threshold for motion, then yes, you draw, yeah, so this rotation is the way you want to turn it. Yep. And the moment that you're calculating is working against you, and it's provided by the bearing. Any other questions about that? So that's kind of like, if you just remember that, there really isn't too much to this derivation. Like you shouldn't have too much trouble remembering how to go if you remember sort of how to set it up. So let me draw a big, like zoom way in on this. So we have the downward force W. And we have the upward force W. Okay, so here's W. And that W is made up of a friction component and a normal component. Okay, so we know the directions of those two, right? The normal has to be this way, and the friction has to be tangent to that surface. These are perpendicular. This component is the coefficient times the normal. And so if we're trying to figure out this angle, that angle is just equal to the inverse tangent of mu n over n which is just the inverse tangent of mu. So why does it help to figure out that angle? Like where are we trying to go with this? Well, all we're trying to do is figure out the moment that this force W applies. Okay, and so to do that, we just need to know what this moment arm length is, right? Like you can think of this as rho. Okay. If we can figure out what this rho value is, then we can figure out what the moment is. And now notice that this theta is the same as this angle. Okay. And this leg of this triangle is equal to, or the hypotenuse of this triangle then, now these are perpendicular, the hypotenuse is equal to r. And so that rho is just equal to r times the sine of theta. Okay, or, you know, r times the sine of the inverse tangent of mu. And you could go through and do, you know, like in, I don't know, pre-calc or calc 1 or something, you had to do all these like manipulations where like you can actually come up with values for this. Remember doing that where like, you know, it's like you're trying to find the sine of an angle that has an inverse tangent of a certain thing. So remember that? Am I crazy? So if the tangent is mu, then you can think of this leg as mu, this leg is 1, because then theta has a tangent of mu, right? And then that means that this is mu squared plus 1 square root. And now the sine, you know, r times the sine of this angle is r times mu, opposite over hypotenuse, over mu squared plus 1. And I guess that's maybe as far as you can go with it. Okay, and now we have the rho vector, or it's just a scalar in this case, and so the moment is equal to W times rho. So the weight times mu r divided by mu squared plus 1 all square root. Okay, so that's a formula, but you have to go through this derivation, and you don't have to derive this formula. If you plug in the numbers that are given, you know, you don't have to do all this manipulation. You just have to come up with a numeric value for any questions about that? Okay, let's do one of those. Okay, so let's say that, so let's say we have a setup like this. And let's say that the load that the axle is holding is, oh, I know what that is. That's Tony Weinbeck playing his electric guitar on the last day of class. But he didn't make his in a 3D printer, loser. Yeah. I didn't know what that was, but yeah, he has his electric guitar in here today. Okay, and so if there's 4,000 newtons on each side of this axle, then that means 8,000 newtons has to be acting up for this to stay in equilibrium. And let's say that it's rotating counterclockwise to somebody over on the right side. What's the torque that must be applied Yes. Let's do it the other way, because we already did one clockwise. Thank you. That must be applied to maintain a constant angular velocity. We have a static coefficient of friction of 0.05 and a kinetic coefficient of friction of 0.02. You can get low values like that with a dry lubricant. Okay, so which coefficient matters to us? Yeah, kinetic, right? And so go to the free body diagram. The axle has two downward forces that total 8,000. The rotation is this way. So which side of the center line does that bearing force have to act to try to slow this motion down? Yeah, it has to be over here. No, the right. So it has to be over here. And we know that this magnitude is 8,000. Let me put this, write this on the other side of that line. And we know that that 8,000 can be broken up into a normal component and a tangential component. I sort of want to go here, Tony, play. So this is 0.02 N. Yeah. 8,000, yes, thank you. Yep. Okay, and this angle is the same as this angle. So to come up with theta, theta is equal to the inverse tangent of 0.02 N over N, and the N's cancel. Can someone calculate that inverse tangent in degrees? What is it? Okay, it will be it will be really small. Like I've exaggerated a lot. 1.15 degrees. Okay, so now rho is this. Okay, this is the rho that we're looking for, the moment arm. So rho is equal to, oh, did I give a, I didn't, dang. Okay, so let's say that this has a diameter of 0.06 meters. Okay, so rho is equal to r times the sine of 1.15 degrees. So that's half of the diameter. So 0.03 times the sine of 1.15 degrees. And can someone calculate that?
6 to 9.
And that's meters. And so the moment produced by that offset in the bearing force is equal to 6 times 10 to the minus 4 times the force of 8,000. And that is 4.8 times 10 to the minus 1 minus so 4.8 Newton meters. Okay, what we really calculated, so the question asks what's the external torque you have to apply to keep it rotating. That's not what we calculated. We calculated the moment that's produced by that offset in the bearing, but the only two things producing a moment on this axle are an external torque that we apply and the torque due to this offset. And so whatever this is, that's what we have to apply to. Do you know what I mean? Okay. Well, you could think of it like this. Think of, so we're trying to calculate this moment M that we need to keep it rotating, right? If we do the rotational equation, there are only two moments acting if our about point is the center. Those are negative M in this, oh no, positive M because it's counterclockwise, and a negative moment of 4.8 Newton meters. It's an equilibrium, so those have to be equal to 0. So our external applied moment has to be equal to 4.8 Newton meters. Any questions about that?
So when you do the free body diagram,
Mhm.
you always look at on the right side?
It doesn't matter which side, really. I, I just was careful about that to try to help you visualize what's going on, but it doesn't matter to me which side you look at. And you're just looking for a scalar value, so I mean, even if we switched everything, this would be over on the other side. We'd still get the same numerical value. Yep.
And if we were to draw that free body diagram like the first one, like you had the 800 force on top of it.
Oh yeah, you know, I guess I don't care about, if you want to just always put it on the bottom, always put it in the same, on the same side on the bottom. That's fine with me.
If we did, it would be just straight across the other side, right?
Yes, that's right. Yep.
So on your last page, you told us that the moment was the weight times the pressure, which doesn't depend on data. We do a row. You don't even need to do all that.
To do what?
Row.
To get rho, you have to know the angle. Yeah. So yeah, you're doing all of that to get an angle just so you can calculate that moment arm. Yep.
In this case, the direction of both forces, the downward and upward,
They're the same. They're both just straight up and down because they have to be equal and opposite in order to have equilibrium.
so the top one, 8,000 is supposed to be up.
Yes.
But in here is the three-point diagram.
I switched it. You're right. Thank you. This drawing. Yeah, thank you. So really it should be like this. And a normal, wait, 8,000. No, 8, okay. Okay, this one, so what I did there didn't change the answers, but yeah, it would be at the bottom. I think this is worth thinking about because this can be sort of hard to visualize if you're not, if you don't get this kind of stuff right. So that contact between the bearing and the axle would be at the bottom, and which side would it be on? It would have to be over here. So, so we'd have an upward force here of 8,000. A normal force here. A friction force here. This angle is theta, and this angle is theta. So that's really what's going on in this. But if you don't want to worry about that and you just say that you don't even want to think about which side any of this is on, you just always want to draw your triangle over on this side with everything in the same orientation and with your force directly on the axle going up, you'll get the right answers, and that's fine with me. Okay. But if you want to make the free body diagram like really accurate, this one would look like this. Any other questions? Okay, let's take, so that's the end of the material for the class. Let's take a 10-minute break, come back, and I'm going to do a couple of just tying things together type things, and then that's it.